I'm currently in the process of moving my CPU build from breadboards to PCBs on a proper backplane. In the previous episode, we have built up this port LED PCB, which sits on top of the stack of registers and simply shows what the data is that comes out of the register file and that goes into the register file. We've also sketched up this rough layout of how the backplanes should look like in a first iteration. And we've been busy building up the left-hand side of the sketch here. The port LEDs we've built up in the previous episode, and the second missing PCB on the left hand side here is the flags and the move immediate buffer PCB. On the breadboard, right next to where the program memory is, we have two tri-state buffers. There's the move buffer, which drives the second operand to the write data port. This allows us to read a value from the register file and then drive it onto the write data port to write it back to a different register. But we also have this immediate buffer here that allows us to drive the upper 8 bits of the instruction onto the RD2 port of the register file. And by disabling the register file's read port and enabling this immediate buffer, we can pick whether the second operand, the one that's transported on the RD2 port, is a register value read from a register or the immediate value stored in the instruction. And these two buffers I would like to move onto a dedicated PCB that sits right below the register file stack because it's very intimately tied to how we read values from the registers and how we write values back into the registers. Since that's only two buffer chips, which doesn't use a lot of space, I've also decided to put the flags register onto this PCB. Currently, the flags register is part of the ALU breadboard, but that's not something I want to have in the PCB version of the ALU, because if we move to superscalar execution or out-of-order execution, we want to have the flags be more or less just another register of the CPU that instructions can read from or write to. So we can use the additional space on this PCB to also accommodate the flags register. Let's go draw up a schematic for this. Let me create a new project and schematic for this flags and move and immediate buffer PCB. Let's start with the move buffer, which is probably going to be the simplest thing. I'm just going to use the 74HC541 buffer again that we've used on the GPR PCB and the port LEDs PCB. And all this buffer did on the breadboard is it read the current value on the RD2 port and drove it onto the write data port if it was enabled. So this PCB is definitely going to need access to the write data port of the register file and the read data port 2 of the register file. And let's hook those up to the buffer. And then we also need to be able to enable and disable this buffer. Right now on the breadboard, we have wired one of these output enables up to an instruction bit. And if that instruction bit is a 0, we're doing a move. And if that instruction bit is a 1, we're doing an ALU operation. And the other output enable, we've tied to 0 to constantly enable it. Here on the PCB, I think I want to expose both of these enable inputs on a pin header, because they are more or less equivalent to a free AND operation for the enables. So I want to connect both of these inputs to a pin on a pin header, such that we have access to them. However, what has happened on the breadboard is that we had to invert some of these enable signals. Now that we're moving things onto dedicated PCBs, I think I want to include these inverters on this PCB here. On the breadboards, we've used the 74HC04 chips, which are just 6 inverters in a package. But those also come in an SMD single gate variant. So let me look for a 74HC1G04. So in terms of control signals, we now have a move output enable 1, which is active high, and we have a move output enable 2, which is active low. Let me also add an LED that will indicate whether the buffer is enabled. We want this LED to light up whenever the move buffer is enabled. So whenever the move output enable 1 is high and the move output enable 2 is low. And that's pretty easy. We just use the move output enable 1 on the positive side of the LED and the move output enable 2, which is active low, on the negative side of the LED. All right, that's the move buffer. Let's also add the immediate buffer. The immediate buffer takes the upper 8 bits of the instruction, the immediate bits on the left-hand side at its input, and it conditionally drives those onto the RD2 port. And we're going to play the same game with the enables here. We're going to have an active high output enable and an active low output enable for the immediate buffer. Now, if you remember, we used to have an add immediate instruction in the CPU. But one of the problems that we've encountered is that the immediate takes up 8 bits of the instruction, the destination register takes up another 4 bits of the instruction, and so that leaves only 4 bits to actually encode an instruction. So in our CPU, we can only have a total of 16 instructions that have an immediate operand and a destination register. So these 8 immediate bits eat up a lot of instruction encoding space, which is pretty valuable. I still want to use immediates in a lot of situations because they're very convenient and they make the instructions very powerful. And in fact, in most cases in practice, we don't need the full 8 bits of the immediate. If we're just incrementing a value by 1 in a register, we only need a few bits of immediates. And now that we're moving things onto a dedicated PCB, I think I want to introduce an immediate mode, which lets you pick between using the entire 8 bits from the instruction as the immediate, or whether you want to just use the lower 4 bits of the immediate and then sign extend to 8 bits. And so here on the PCB, we don't just want to directly forward immediate bits 4, 5, 6, and 7 to this buffer, but we want to run those through a multiplexer. So let me add a 74HC157 multiplexer chip, which has 4 2-input multiplexers, exactly what we need. And we've already used those chips in the program counter PCB quite a bit. And let me pick immediate mode 0 to be the 8-bit immediate mode, and immediate mode 1 to be the 4-bit immediate mode. So the inputs 0 of the multiplexer, I'm going to hook up to the plain old bits 4, 5, 6, and 7 of the immediate. And then when you select mode 1, we want to sign extend the lower 4 bits, which means we're going to take immediate bit 3, the topmost of the lower 4 bits, and we're just going to replicate it across all the upper bits. And in theory, this enable input would be a way to make the upper 4 immediate bits read as a 0, which can be useful in certain corner cases maybe, but I don't see any use for my CPU here. Let me also add an LED to the immediate mode, such that we can tell what the buffer is doing. And the immediate mode is going to be yet another control signal for this PCB that we can hook up on the backplane. And so the only thing left is the flags register. We have 4 flags in total, so even though you could get register chips that have just 4 or 6 bits, which would be more suited to the task, the HC377 is the only register that I have access to that actually comes with a proper clock enable. And that is very handy for this kinds of applications because you don't want to put any logic into your clock tree without being very careful and also including a proper latch to suppress any kinds of glitching on the clock line. We might have to do that in the future for certain parts of the CPU, but definitely not today. And so this flags register will produce the current value of the flags at its output, and it will read the next value that the flags should have at its input. So these are like a flags write data bus and a flags read data bus. Let me also add an LED that shows us whether the flags write enable signal is active. And I think we also want 4 LEDs that show us the current state of what's in the flags register. Basically similar to what the regular register PCBs have, but we just need 4 LEDs. And this flags write enable signal is yet another control signal that we'll want to connect to on the back plane. So these 6 control signals will go onto their own dedicated control pin header. And we also need a connection for power and ground and the clock. I'm going to use the same pin header that we used on the general purpose register, which will make it easier to line everything up. And we'll also want some decoupling capacitors. We have 1, 2, 3, 4 larger chips, and these inverters are going to be close to the corresponding buffer. So let me add 4 100 nanofarad decoupling capacitors. Let's see if we're missing any connections. Looks good. So let's move over to the PCB layout editor. First up, let me roughly create a board outline and align the pin headers with the rest of the register stack. And since this is the last PCB at the bottom of the register stack, I'm gonna put the write data and read data port connections at the top. Okay, I think that's roughly a layout we can work with. Let me move the buffers close to the ports that they're driving, and let me arrange the rest of the components. I think I'm going to flip the order of the flags in a few places, such that flag 0 is at the right and flag 3 is at the left to match what we have on the breadboard. It looks like it would be useful to reverse the pin order on this buffer chip here, and probably also on this buffer. Yeah, definitely. Yeah, that looks a lot more routable. Okay, so that's the board roughly laid out, and the RD2 bus also routed horizontally across the board. Let's do some more detailed routing. Alright, this is starting to look pretty good, and that's most of the signals routed, I think. Let me go check which signals are still missing some routes. Looks like it's just the power and ground connections. These will add later on with a copper fill. Let me clean up the Silkscreen a bit and add labels for the pin headers. Let me add the logos and then do a few finishing touches. Alright, let's finish up by adding copper pores to the top and bottom layer. The top layer will be VDD and the bottom layer will be ground. Let me also make sure that there are good power connections across the signal traces, because these tend to split the copper pores into disjoint islands. Okay, that's all the nets routed. Let me take a quick look at the 3D preview to get a feeling of how this will look. This looks pretty decent. Let me order this up and then let's go assemble the PCB once I get it back from the manufacturer. Alright, I've got this in the mail. PCBs and a stencil for them. Let me apply some solder paste to the PCB. That doesn't look too bad. And now let me add the components. I'm going to start with the smallest one, the capacitors. Then I'm going to add the resistors for the green LEDs. And the red LEDs also need a resistor. Then let me add the red LEDs. And then the green status LEDs. Next up we have the two single gate inverters. And then we also have the two buffer chips. And finally the register, which stores the flags. And I almost forgot, we also have a multiplexer chip in the bottom right. Alright, that looks pretty good. Let me turn on the hot air gun and solder this up.
Alright, that looks pretty good. The only thing left to do is to add the pin headers to the PCB. And I'm going to use James Sharman's technique again. I'm going to use more of the same PCB as a jig to mount the pin headers in. I'm quickly going to give this a quick cleanup and check off camera. And then, let's see if it works. Let me mount the PCB onto breadboards such that we have easier access to the pins. And we'll want to be able to look at the write data and the read data bus, so let me add a few LEDs to those. And I'm going to add a pull-down resistor to the immediate input. And the board needs some power. Let me tie the clock low for now, and let me disable all the control signals. First, let me try to write a 0 into the flags register. To do that, I'm going to connect the flags write data port to all zeros. Then we need to activate the flags write enable signal, which activates the flags write enable LED. And when I toggle the clock now, the flags register clears to 0. And I can now connect a different pattern and then toggle the clock again. And the pattern gets stored in the register. However, when I change the pattern again, but deactivate the flags write enable signal and then toggle the clock, nothing happens to the flags register. But when I set the write enable signal again, the register updates to the all 0 value I've connected. So it looks like the flags register is working, which is a nice isolated component of this PCB. Next up, let's see if we can make use of the immediate buffer. Let me connect the bit pattern to the immediate input. And when I activate the two immediate output enables, the immediate output enable LED goes on and the pattern gets pushed onto the read data port 2 signal. And as long as the immediate output enable is active, I can change the pattern on the immediate input, which will show up on the RD2 port immediately. In addition to what we had on the breadboard, this PCB now also has an immediate mode select signal, which can switch between 4 and 8-bit immediates. Currently the immediate mode is 0, so all 8 bits of the immediate get forwarded to RD2. Let me change this to immediate mode 1 now, which turns on the immediate mode LED, and as you can see at the output, we now get a 4-bit sign extended immediate. So the lower 4 bits of the output still correspond to the lower 4 bits of the immediate, but the upper 4 bits are basically just copies of bit number 3 of the immediate. And so here all upper bits are set because the topmost bit of the 4-bit immediate was set, but when I clear that to 0, you can see that the topmost 4 bits also turn off. And by toggling this immediate mode signal, I can select between an 8-bit immediate or a sign extended 4-bit immediate, which is going to be very handy. We also have 2 enable signals for the immediate buffer. So if I turn either one of them off, you can see that the immediate buffer gets disabled. That's pretty cool. But besides the immediate buffer, we also have a move buffer on the PCB. Let's give that a try. Let me connect the pattern to the RD2 port. And if I activate the 2 move enable signals, you can see that the move output enable LED goes on and the pattern that I've connected to the RD2 input shows up at the write data port. And again, if I change the pattern, the result will immediately show up on the write data port. Also, just like with the immediate buffer, the move buffer also has 2 enable signals. So when I deactivate either of those control signals, you can see that the move buffer gets disabled. Okay, pretty sweet. That seems to be working like a charm. we now have the flags register, the move buffer, and the immediate buffer, plus an additional immediate mode selection on this single PCB. And instead of having these buffers distributed across the system, they will sit neatly below the register file stack and do their thing. In the next episode, I think I want to try and build up a backplane for the register file, where all the PCBs we've been building in the past can sit and form a complete register stack. And that will allow us to get rid of quite a few things on the breadboards and replace with a proper PCB. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.